Hello, ladies and gentlemen. My name is Shuo and I'm from Stuttgart University. Today, I'd like to present our new research about ultra-thin image sensor chip embedded foil, which is a part of DFG project FlexCom. In the next session, I'll give you an overview of the FlexCom project, and it will be covering these next 3 key points. What is a chip film patch technology? Which thickness we achieve, which interconnection problems we had, and how did I solve it? This project has 3 partners, INES, IHF, and INT. The 3 institutes are working close together to develop a whipper system in foil, comprising an image sensor, IF chip, and the antenna. The whole system is packaged in polymer foil and has only 17 micrometer thick. It is mechanically flexible and environmentally agnostic. To produce HiSafe, we developed chip film patch process, a wafer-based technology in which the ultra-thin chips are embedded in flexible polymer foils and electrically connected with metal tracks. With this technology, silicon chips with structures of a few micrometers can be integrated into large area film systems. In order to investigate if the chip film patch technology has an influence on the image sensor performance, the experiments were divided into 3 groups. Group 1 is a standard reference image sensor. When the image sensors in group 2 were thinned down to 30 micrometers. In group 3, the thin chips were mounted on a polymer foil using chip film patch technology. All the 3 groups used the same ceramic package and were applied with the same measurement on a test board to get their transfer and sensitivity curves. Obviously, the measurement results show that the ultra-thin image sensors in foil have comparable characteristics to the non-thin reference chips. At the beginning of our project, we had interconnection problems from time to time. The reason is, in order to minimize the foil system thickness and the step between the top of the chip and the wafer surface, we have to sink chips into a deep cavity. However, this creates problem. The metal circuit will be broken if the chip edge and the cavity are separated by a deep trench. My solution is to use capillary force to planarization the trench. We know there are 3 major forces acting on film during a spin coating process on the surface with topograph and trenches. They are gravity, centrifugal force, and capillary force. Gravity and centrifugal force are due to the spin coating parameter unchangeable, so capillary force plays a role. This force can suck the material into the trench. Several experiments with different trench size were done. The goal is to achieve 100% planarization level, which means the trench was fulfilled with materials. As an example, you can say there's no trenches anymore with a 12 micron dips and 40 micron width cavity. In my last foil, I'd like to show you some good production using chip film patch process. They are optical profilometer results of an embedded foil, an IF chip connected with antenna, and the foil system with an image sensor connected by a connector for further measurements. This is the end of my presentation. Thank you very much for your attention. Goodbye.